We're on FRQ topic 2. This is graphical analysis. And just a quick look at the most recent years that this was seen. You can, on the AP exams, you can see that this is a very, very common topic to be covered. And you'll see why. This hits on, absolute max, min, relative max, min, increasing, decreasing, points of inflection, concavity. It hits on all of those very important concepts that we talk about in calculus. So it's no wonder that this appears so often. The fundamental theorem of calculus is often seen on these types of questions. We're very familiar with the first fundamental theorem of calculus. We use it all the time. We use it every time we have a definite integral. We use the fundamental theorem of calculus. The second version of the fundamental theorem of calculus is the one that I need to refresh you on. If we have, if we are taking the derivative of an integral, that is our second fundamental theorem of calculus. The derivative of an integral, and I'm going to be putting boundaries on here. I'm just going to call this f. I'm going to put boundaries, and these boundaries might have an x in it. Actually, they will have an x in it. So I'm going to call this f of t. So this is some function with t's in it. And I'm going to begin with the most broad version of this theorem, where the lower boundary is some function of x, and the upper boundary is some function of x. If you're taking the derivative of this integral, I think to myself, it kind of cancels out. The derivative of an integral kind of cancels out. This is going to equal, I begin at the top boundary, and I take its derivative. This is the step that people tend to forget. Take its derivative. And then you multiply by, you replace every t in this function with that h of x. So f of h of x. Then you move into the bottom boundary. So we're going to subtract. We begin by taking the derivative of that bottom boundary. And then multiply by, replace t with that bottom boundary. And that is the second fundamental theorem of calculus. We often see one of these boundaries be a constant, maybe a 3, something like that, whatever, some constant. And then this upper boundary, a lot of times we see it just to be an x. So if you have that, we begin at the top. We're taking the derivative of an integral. This only works if you're taking the derivative of an integral. The derivative of x is just 1. Replace t with x minus the derivative of 3 is 0. So this will be just f of x. And we see this version a lot in these types of problems. Every once in a while I have seen them do something like a 2x or an x squared or something like that up there. And if they do that, just don't remember that you have to multiply by the derivative of that first and then replace your t with that 2x. The bottom boundary the derivative of the bottom boundary is 0, so that doesn't even make an appearance here. All right, let's take a look at some examples, see how these are presented. And I think you'll recognize this, hopefully you'll recognize this when I show you an example. Okay, let me grab this packet. Okay, we're gonna do a few odds together today. Well, in this packet, it's the odds. This first one is from 2018. So if it's not number 1 in your packet, go find 2018. This was number 3, so no calculator. These will be no calculator. These are always a no calculator question. So put your calculator to the side. All right, we have a continuous function, the graph of a continuous function g, which is the derivative of f, is shown. So g is the derivative of f. So I might come over here and say f prime. G equals f prime, the derivative of f. The function g is piecewise linear. That just means between x equals -5 and 3, we have little line segments. And sure enough, I look over here, and between -5 and 3, we have little line segments. And then they give me an equation for g for 3 to 6. So we have that little parabola from 3 to 6. Okay, part A. If f of 1 is 3, find the value of f of -5. Very straightforward fundamental theorem of calculus question. So I'm going to set up the fundamental theorem of calculus. F of 1, always start with your higher x value. F of 1 minus f of -5 is equal to the integral from -5 to 1. Remember, your whatever value of x you have here must go as your top boundary, of f prime. You can call it t's or x's, it doesn't matter. Does not matter. I'm going to call it x's because I see that's what they want me to use here. All right. So this is g of x. In fact, I will say f prime of x is equal to g of x. We really don't have to write that there because they told us that. So we really don't have to write that there this time. All right, we're solving for f of -5. So if I move that to the other side, it'll be positive, so I'm going to be subtracting the integral. This is going to be f of 1, which is 3, minus that integral, minus the integral from -5 to 1. So we're looking at areas from -5 to 1. So the first section is below the x-axis, so it's going to be a negative. And I would probably just do this big 3 by 3 square and make that a -9. And then this is a little triangle. It's still negative. It's still below the x-axis, so we make it negative. 1/2. The base is 1. The height is 3. So that takes care of that little trapezoid there. From -1 to 0, we have no area. And then from 0 to 1, we're above the x-axis, so the integral is going to be positive. It's another little triangle. 1/2. The base is 1. The height is 2. Like that. And that is the value of f of -5, and I'm going to safe stop right there. There's unless I need it later, I'm just going to leave it like that. Part B. Oh, and that was 2 points. That was worth 2 points. The first point was for the integral. So the first point was for our integral, and the second point was for the answer. So just 2 points there. Part B. Evaluate the integral from 1 to 6 of g of x. Okay, from 1 to 6. So I'm looking over here, from 1 to 6. Ah, I see. I have, for this piece, I can use the graph and count the squares. For this piece, though, I'm going to need to do an integral using the equation for g of x. So, step 1 is going to be splitting this integral up into its 2 pieces. From 1 to 3, and from 3 to 6. So from 1 to 3, that's equal to 4. Positive 4, it's above the x-axis, so positive 4. From 3 to 6, though, I'm using the equation for g in that interval, so it's going to be 2 times x minus 4 squared dx. We can either do a little mental u sub here, or you could actually FOIL this out and multiply everything by 2. However you want to do that is fine. I'm going to do a little mental u sub because the derivative of x minus 4 is just dx. So I'm treating this like a u. And this would be, it's u squared, so it'd be raise the power by 1, and we'd have u cubed, and then divide by that new power, and then we're integrating that from 3 to 6. That 2/3 can come out, put 6 in for x, I'd have 2 cubed. Put 3 in for x, I'd have a negative 1 cubed. And that's a safe stop spot right there. I always encourage you to safe stop when you can safe stop. Why risk making an addition or multiplication error? Okay, numbers up. Oh, how much was that worth? That was worth 3 points. The first point was for splitting that integral at x equals 3. So splitting that integral was just worth a point, right, just from splitting that. 1 point for the antiderivative of 2 times x minus 4 squared, and then 1 point for your answer. Okay, part C. In between -5 and 6, which is the entire domain here, on what open intervals, they're telling you to make open intervals, so we'll make them open, if any, is f both increasing and concave up. And then we have to justify our answer. So I'm going to say f is increasing when f prime is positive, right? And we have the graph of f prime. We can see all the sections of the x values where f prime is positive. F is concave up when f double prime is positive, meaning the slope of f is positive. Okay? So we want for f prime to be positive and f double prime to be positive, the slope of f to be positive. I'm sorry, the slope of f prime. Sorry. F double prime is the slope of f prime. Yes. And we have the graph of f prime. So we want for f prime to be positive and its slope to be positive. So we're talking about this region, this section. So from 0 to 1 and from 4 to 6. So f is increasing and concave up on 0 to 1 and 4 to 6. Okay? On the AP exam, you will write out these words. Okay? Avoid giving our cutesy little abbreviations, right? Take the 2 seconds to write out those words, just in case. All right? That section was worth 2 points. 1 point for the intervals, 1 point for the reason. Part D. Find the x-coordinate of each point of inflection of the graph of f. So f has a point of inflection when f double prime changes signs. That's when f has a point of inflection. We've already said that f double prime is the slope of f prime. So we want for f to have a point of inflection, we want f double prime to change signs. So let's come up here. We want the slope of this to change signs. Okay, right here, the slope did not change signs. The slope went from 0 to positive. That's not a sign change. Right here is not a sign change, not a sign change, not a sign change, not a sign change. Here's a sign change. This is the only x value that f double prime changes signs. So f has a point of inflection at x equals 0. And my reason is what I said right here. That was worth 2 points. 1 point for the answer, 1 point for the reason. We always justify our answers, okay? All right, next up we're going to take a look at in this packet number 3. This is the question from 2016, number 3, no calculator. Let's see what it says. The figure shows the graph of the piecewise linear function f. From -4 to 12, the function g is defined by this. Okay, as soon as I see that, I know I'm going to need g prime, and I know I'm going to need g double prime somewhere. Okay? So I like to go ahead and say it here. G prime is the derivative of that integral. Here's our second piece of the fundamental theorem. This will just be f of x. The derivative of x is 1. Put in x for t. The derivative of 2 is 0. G double prime then will be f prime of x, which is the slope of f. So now I know that this is the graph of f, which is g prime. And the slope of this will be g double prime. Okay, part A. Does g have a relative min, max, or neither when x is 10? I look up here when x is 10, and I see that g prime was negative before x equals 10, and it's still negative after x is 10. G prime is negative down here because this is the graph of g prime, right? So this is neither a max or nor a min. So I'm going to say g has neither a max, a relative max, nor a relative min when x equals 10, since g prime does not change signs when x is 10. Okay, that's not the only way we could say it. We could have done the second fundamental theorem there as well, but this will work. That was worth, let me get to our, that was worth, well, it was worth 1 point. Answer with justification. But also up here, on here, they say, in the problem, they say there's 1 point awarded for stating g prime is equal to f in any of the parts, in A, B, C, or D. So as long as we mentioned it somewhere, that was worth a point. All right? We mentioned it first thing, so we're in good shape. Part B. Does G have a point of inflection when x is 4? Well, I look up here when x is 4. When x is 4, I see that the G double prime, the slope, is changing signs. Point of inflection is when the second derivative of this changes signs. So yes, we do have a sign change there. So I'm going to say G has a point of inflection. You would write that out. When x is equal to 4, since G double prime changes signs there. And I've already said what G double prime is, so I don't have to state it here. If I had not stated this here, I would have had to state it here. Okay? That was worth just 1 point. Answer with justification. Part C, find the absolute minimum value and the absolute maximum value of G on that interval and justify. So when I see absolute min-max, I think closed interval test. So my independent variable here is x. I'm finding the max and min of G, so that goes here. I begin with my closed interval boundaries, -4 and 12. And I also put here any critical values for G, specifically any possible absolute mins and max x values, which means I want relative min x values here. Okay, so I'm going to say G prime equals 0 when x equals, I always tell AP what you're doing. Don't just throw numbers here without saying why you're doing that. Okay? These came from the closed boundaries, and that's fine. You don't have to say where those are from. But here you need to say why you're putting numbers here. G prime is 0 when. So G prime is 0 when x is negative 2, 2, 6, and 10. Negative 2, 2, 6, and 10. Okay. However, when x is 2, we do not have a relative min or max because G prime stays positive. It did not change. G prime does not change signs there. Same thing at x equals 10. G prime does not change signs here. So the only possible absolute max and min would be when x is negative 2 and 6, in addition to our boundaries. So I'm going to say G prime changes signs when x equals negative 2 and 6. Those were our two sign changes. So negative 2 and 6 need to go here. Now, if you want to put these other two values there, that's fine, but you don't have to, okay? The only values of x, these are the candidates for the absolute min and max. So you would not need to put a candidate here if it's not a candidate, an x value here if it's not a candidate. Okay, now we just need to find these g values. Need to find the g values. So let's see. How are we going to find these g values? Well, I'm looking up here because lots of times they give us a point. They give us a g value, but here they did not give us a g value. Instead, we're going to need to use an appropriate g value that we know this integral for, and that value of x would be, not g value, the x value where we can get the value of g. The x value would be a 2. If I put a 2 in for x, I know that this integral is 0. That will be our starting g value. So I'm going to say that g of 2 is the integral from 2 to 2. I'm just copying that down. I'm putting 2 in for x. So the integral from 2 to 2 is 0. That was not one of my values here. It was one of our critical numbers, but we don't have to put it there. But we certainly can. All right, so from there I can use my fundamental theorem to get these remaining values. So I'm going to start with the negative 4. I'm setting up the fundamental theorem, so g of 2 minus g of negative 4 is the integral from negative 4 to 2 of g prime, right? G prime is our function f as well, right? So this gives us that g of negative 4 is equal to, and again, I'd be bringing that to the right to make it positive, and I'm subtracting the integral from g of 2. G of 2 is 0, so that's just going to be negative the integral. Negative that integral from negative 4 to 2. From negative 4 to 2, this area is negative, and it's the same as that area right here, right? So those cancel each other out, and I only have this area left. It's going to be a positive because it's above the x-axis. 1/2 2 times 4. 1/2 2 times 4. So this will be a negative 4. So when x is 4, g is negative 4. And then we have 3 more to do here. G of 12 minus g of 2 is the integral 2 to 12 of g prime of x dx. So g of 12, this g of 2 is just 0, is equal to just that integral. So the integral from 2 to 12, right here. Well, I see this area will cancel out with that area, and my only remaining area will be below the x-axis, so I'm going to make this negative. Negative 1/2 2 times 4. Negative 1/2 2 times 4, which is negative 4 again. Did I do that right? Oh, I'm so sorry. 2, yeah, I did that right. 2 times 4 is negative 4. Okay, so negative 4 comes up here. So now we're doing g, I'm going to do g of negative 2. So I always want to put my larger x value first, especially when I have a graph I'm reading. So negative 2 to 2, g prime. I'm solving for g of negative 2, so again, I'm bringing it to the right, making it positive, and bringing the integral to the left where it'll be negative, negative, and then we have negative 2 to 2, which is all above the x-axis, and that will be, I know that, now I know each of these little pieces is a 4, so that will be an 8. So that's a negative 8. Lots of negatives so far for our g values. Lastly, g of 6 minus g of 2 is the integral from 2 to 6 of g prime. So g of 6 will be, and I'm 2 to 6. 2 to 6 is positive this time, that positive 8. So we finally have a positive number here. All right. So my absolute min, and remember that you will have lots of space on the actual exam. The absolute max, G has an absolute max. We want the absolute max and min value, the value. So the absolute max of 8 and an absolute minimum of negative 8 by closed interval test. Okay. All right. That was worth 4 points. 1 point for considers x equals negative 2 and x equals 6 as candidates. 1 point for considers x equals negative 4 and x equals 12 as candidates. And 2 points for the answer, actually answers, with justification. Okay? All right, part D. In between negative 4 and 12, find all the intervals for which g is negative. G is negative. Not g prime, just g. We found lots of g values up here, and I remember I even made the comment, we have lots of negative values there. But then we had this positive value of an 8. So let's think about that. I'm kind of wishing that I had found I had gone ahead. I do know that g of 2 is 0. I know g of 2 is 0. I wish I had found g of my 10 out here. G of 10 would be the integral from 2 to 10, right? G of 10 would be the integral from 2 to 10. So that would be 0, right? That zeroes out. So f of 2 and g of 2 and g of 10 are both 0, right? So it tells me that if I were to just like sketch out a little graph, 2, 4, 6, 10, 12, all the way over there. Wait, 2, 4, 6, 8, 10, 12. Okay. So when at negative 4, g is a negative 4, but then at negative 2, g is a negative 8, right? At 0, g, it makes sense to me at 0, we didn't find it, but at 0, it makes sense to me that we would be, since g prime is linear, we have a similar rate. It's changing at the same rate, right? So it tells me that here at 0 we're going to be back to a -4, and then at 2 we'll be up here at 0, which we know that's a point. I know at 10 we're at 0 as well. And then from 2 to 6, G prime is positive, so I'm increasing. From 2 to 6, I'm increasing. So from 2 to 6, I'm increasing until I get to 8. And then from 6 to 10, I'm decreasing until I get to 0. And then from 10 to 12, I continue to decrease. So I'm thinking this goes something like that. We did not have to justify, thank goodness, because this would be hard to put into words. It would be hard to put what we did here into words. So they did not have us justify, they just want the answer. So G is negative, or equal to. So we're going to get these equal to's as well. From -4 to 2, and from 10 to 12. That's when we're negative. We did not have to justify it. Okay? That was worth 2 points for the intervals. And that's how that question was scored. So that was number 3. Let's go take a look at number 5. Bouncing around to some odd problems. Well, number 5 on here, this was 2013, number 4. So if you have a different packet, go grab 2013, number 4. All right. The figure shows the graph of f prime. So here they tell us this is f prime. The derivative of a twice differentiable function f. Okay. The graph of f prime has a horizontal tangent at x equals 1 and 3. Okay, so we have a horizontal tangent at x equals 1 and x equals 3. Oops, that's not x equals 3, that's x equals 5, right here, x equals 3. Oh, and x equals 5. Okay, perfect. Okay, great. The areas of the regions are labeled, all right, and they give us a value of f. That's nice of them. All right. Find all the values of x in the open interval for which f has a local min, and justify your answer. So in my mind, when I hear f local min, I think f prime negative to positive. That's in my mind, I'm thinking that. So I want f prime to go from negative to positive. This is the graph of f prime. I'm looking for where it goes negative to positive, and right here, f prime goes negative to positive, below the x-axis to above the x-axis. So f has a relative or local min when x is equal to, that's 6 for x. Since f prime goes from negative to positive. On the AP exam, again, you're going to write out the word negative and you're going to write out the word positive. Okay? I'm just trying to make these videos as brief as I can, believe it or not. Okay. This one was worth 1 point. Answer with justification. All right. Part B. Determine the absolute minimum value. Absolute minimum value. So on this closed interval. So closed interval test, we're finding the minimum value of f, so f goes on our closed interval chart. We write our boundaries, and then we write any relative mins. Relative mins. So f prime goes from negative to positive at x equals 6. So 6 is going to go on my closed interval test. Could we put the other times when f prime is 0? I'm sorry, at 1, yes, 1 and 4? Yes, you can, but they're not going to be. How could it be an absolute minimum if it's not even a relative minimum? Or a boundary. It might be a boundary. But we certainly wouldn't have an absolute minimum anywhere other than a boundary or a relative minimum. It just makes sense. So I need f of 0, f of 8, and f of 6. I have a f of 8. They gave me that was 4. I'm going to use the fundamental theorem to get the remaining values. So f of 8 minus f of 0 is the integral from 0 to 8 of f prime, which means f of 0, if I take it to the right, it's going to be positive, so I subtract the integral, will be f of 8 minus the integral from 0 to 8. And from 0 to 8, the integral, they gave me these areas. So it'll be 2 plus 6 minus 3, we're below the x-axis, plus 7. And since I need to compare this, I need to go ahead and work this out. So let's see, this is 8 plus 7 is 15, minus 3 is 12, 4 minus 12 is a negative 8. And I would take a second because I would make sure that I did that correctly, since it does, that's going to affect my answer here. Okay, so make sure we did that correctly, and then we're going to go and do the same thing for f of 6, 0 to 6. So f of 6, okay, well, I was going to use f of 8 here, but that's okay. I used f of 0 and set it up like this. So f of 6 will be, I'm moving f of 0 to the right, so I'll have a negative 8 plus the integral from 0 to 6. And the integral from 0 to 6 is 2 plus 6 minus 3, right? 2 plus 6 minus 3. That's 8 minus 3 is 5. Negative 8 plus 5 is a negative 3. I would double check that and make sure I did that right, because that's where I tend to make my mistakes. So the absolute minimum value of f is negative 8. Okay? That was worth 3 points. Let me try to squeeze that in. That was worth 3 points. 1 point for considers x equals 0 and 6. 1 point for the answer. 1 point for your justification. Our justification was the closed interval test that we showed right here. So I remember I don't have to say by closed interval test because it's right there. Okay. On what intervals? On what open intervals is the graph of f both concave down and increasing? All right. F is increasing when f prime is positive, right? F is concave down when f double prime is negative, meaning the slope of f prime is negative. So I want f prime to be positive. F prime is our graph. So I want the graph to be positive above the x-axis, but I want the slope to be negative, going down. So let's find out where that is. I'm only above the x-axis, and my slope is negative. So between 0 and 1, between 3 and 4, and that's it. 0 and 1, 3 and 4. So f is increasing and concave down on 0 to 1 and 3 to 4. My explanation is right here. So that was worth 2 points. 1 point for the answer, 1 point for the explanation. Part D. The function g is defined by this. If f of 3 is negative 5/2, find the slope of the line tangent to g when x is 3. So they want g prime at 3. We're going to begin by finding g prime of x. Well, g of x is this, so g prime of x, we just need a little derivative. We need to use the chain rule here. 3 times your leading coefficient, decrease your power by 1, keeping your same inside, and then multiply by the derivative of your inside. Chain rule. Now we're going to put 3 in for x. F of 3 is our negative 5/2. F prime of 3, f prime of 3, this is the graph of f prime of 3 is 4, and we're done. Save stop. Okay, these I think many of my students get a large number of points on these questions. By the way, this was worth 3 points. 2 points for finding g prime of x using the chain rule, 1 point for the answer. So these graphical analysis questions I think are big point earners for most of my students. Get good at these because we know it's very likely going to be on the test. Very, very likely going to be on the test. Even last year, the questions, there was a big graphical analysis question even in the 2020 test where we were all online. So big topic. Make sure you master it.